Light. It's an electromagnetic wave blasting through space at a staggering 300 million meters per second. But what happens when that literally unstoppable force hits an immovable object? Well, welcome to this explainer. Today, we're going to unravel the incredibly cool geometric secrets of light and see exactly how its physical bounce shapes our perception of the entire world. Now, to kick things off, have you ever actually stopped to ask yourself, how does a simple piece of glass manipulate reality? I mean, how does it show us what's directly behind us or capture the incredibly faint light of a distant galaxy? We totally take mirrors for granted every single day, but the physics governing them is this wildly elegant dance of geometry and waves. So here's our roadmap for today's deep dive. We'll hit the laws of reflection, check out the anatomy of spherical mirrors, explore concave and convex mirrors, lay down the Cartesian sign convention, and wrap it all up with the mirror formula. Let's get right into it. Okay, Section 1, the laws of reflection. Before we even touch on mirrors, we really need to define reflection itself. Simply put, it's just light waves bouncing back into their original medium after hitting a boundary. See, because light can travel perfectly well through a vacuum, when it finally slams into a highly polished boundary, all that energy has absolutely nowhere to go but back. Think of it kind of like a beautifully rigged game of geometric pinball, where every single bounce is 100% predictable. And that's because two unbreakable laws govern this whole process. First off, the incoming ray, the outgoing ray, and that imaginary perpendicular line between them, what we call the normal, they all exist on the exact same flat plane. Second, and this is the really profound one, the angle of incidence perfectly always equals the angle of reflection. Now, here's a crucial point. While both of those laws are strictly obeyed absolutely everywhere, the image you actually see depends entirely on the microscopic topology of the surface. So smooth surfaces, like polished glass, give us incredibly clear specular reflections, mostly because all those parallel light rays bounce back perfectly together in sync. But rough surfaces, even microscopically rough ones, like paper or wood, they scatter the light in a diffused reflection, sending those bouncing rays off in a million different directions. Moving right along to Section 2, Anatomy of Spherical Mirrors. To really visualize how curved mirrors work, you've kind of got to imagine slicing a piece right out of a hollow glass sphere. The pole is the exact dead center of our glass slice. The center of curvature is the absolute center of that imaginary larger sphere we just cut from. Draw a straight line through both and boom, you get the principal axis. Now, exactly halfway between them sits the principal focus. This is the magic spot where light rays either converge together or appear to diverge from. And that distance right there, from the pole to the focus, that's what we call your focal length. Which brings us to Section 3, concave and convex mirrors. Armed with that anatomical map, let's contrast our two primary geometric shapes. First up, the concave mirror. It's exactly like a cave. It curves inward. And because of that specific curve, it acts as a converging mirror, taking parallel light rays and forcefully focusing them inward to a sharp, intense focal point. On the flip side, we have the convex mirror. This one bulges outward toward the light source. It's a diverging mirror. It essentially forces parallel light rays to scatter and spread outward, tricking our eyes into thinking they're originating from a virtual focus hidden somewhere deep behind the mirror itself. So, how do we predict exactly where an image is going to form? Well, it's basically a cheat code with three simple ray tracing rules. Rule 1, a ray coming in parallel to the axis bounces directly through the focus. Rule 2, a ray passing through the center of curvature boomerangs straight back along its own path. And Rule 3, a ray hitting the pole directly reflects off at an identical oblique angle. All you have to do is intersect just two of these rays, and right there is exactly where your image magically appears in space. As you can see from the data here, the concave mirror, it's an absolute optical chameleon. Depending entirely on where you place your object, it can project a tiny, upside-down real image of a distant star, or if you move that object right up close, say between the pole and the focus, it suddenly creates this massive, magnified, upright virtual image. It's seriously incredibly versatile. But then you have the convex mirror. In stark contrast, this thing is fiercely consistent. It literally does not matter where you place an object in front of a convex mirror. Whether it's an inch away or a whole mile away, the image it produces is always going to be virtual, always upright, and always shrunk down to a smaller size behind the mirror. And this isn't just theoretical math, right? This is exactly why these specific geometric shapes govern our everyday lives. Because concave mirrors can focus light so intensely, We use them to capture faint starlight in giant telescopes or to throw those powerful beams from your car's headlights. Meanwhile, because convex mirrors constantly shrink images down, they give us a massively expanded field of view. That's what keeps us safe on the highway with our rear-view mirrors, or keeps an eye on things as security mirrors in hospitals and corner stores.
Okay, let's look at Section 4, Cartesian Sign Convention.
To keep all this light-bending geometry from just turning into total mathematical chaos, we establish some ground rules. We treat the mirror's pole as the exact origin point, 0, 0, of a standard XY graph. Light is always assumed to come from the left. Therefore, any distances to the left of the mirror or anything sitting below the principal axis are mathematically negative. Conversely, distances to the right or above the axis are positive. Now, this right here is a really common trap that catches so many people off guard. But if you just lock in this simple grid in your mind, the math becomes absolutely foolproof.
Finally, Section 5, the mirror formula.
All of this geometry, the rays, the shapes, the angles, it all culminates right here in the mirror formula. It's this brilliant, heroic equation that literally calculates physical reality. 1 divided by v, which is our image distance, plus 1 divided by u, the object distance, always equals 1 divided by f, the focal length. It mathematically links the physical curvature of the mirror with the precise real-world location of the object. And tied directly to that is the concept of lateral magnification, which basically just tells us how big the image is actually going to be. The magnification, m, is the ratio of the image height to the object height, which neatly happens to also equal negative v divided by u. Here's the trick. If your final result is a negative number, it immediately tells you your image is real and upside down. But if it's positive, boom, the image is virtual and standing upright. So let's actually put this to the test and literally solve for reality. Imagine you've got an object sitting 15 centimeters in front of a concave mirror. So following our convention, u is negative 15. Let's say the mirror's focal length is 10 centimeters, which since it's concave and in front is also negative. Plug those into our neat little formula, and we find that v equals negative 30. That means the image forms 30 centimeters in front of the mirror. Now we calculate magnification. Negative v over u gives us negative 2. In a fraction of a second, the math literally proves that your reflection is going to be exactly twice as large and completely upside down. How cool is that? So to wrap up this explainer today, I really want to leave you with a bit of a provocative thought. By applying just a few foundational rules and a single, incredibly elegant formula, we can effortlessly predict the exact path of bouncing light to reconstruct our physical reality. So, if simple geometry can perfectly decode the everyday magic of mirrors, what other completely unseen forces shaping your daily reality are just waiting out there to be decoded with math? Keep wondering and definitely keep looking deeper into the reflection. Thanks for joining me.